The statistical tests that we've used up until now have been tests that used ratio or interval data. The next two chapters, 17 and 18, will use nominal data. And right away, you'll see we don't have means, we're not dealing with standard deviations, we're not dealing with standard errors of measurement or variances or sums of squares, because our data are categories, our data are frequencies, our data are counts. There are interesting analyses that you can do with nominal data. In Chapter 17 and Chapter 18 are about using nominal data to make some inferences about populations. I thought I'd approach the next two chapters differently with the chi-square presentations and go right to solving problems and talk about how I'm solving the problems and try and bring about a good understanding of the chi-square statistic and the binomial test by doing the actual problems themselves. After the problems are done, you might want to go back over the PowerPoints, and every point that's made on the different slides in Chapter 17 and 18, I'll have demonstrated on the problems themselves. So let's do that. Let's advance to the last three slides and go about solving some chi-square problems. Chapter 17 explains that there are two major types of chi-square tests where we're using nominal data or frequencies to do a particular type of analysis. One type of chi-square test is called a goodness of fit test, and the other type is called a contingency table analysis or a test of independence. The goodness of fit tests come in two varieties. One goodness of fit test has, or we expect, equal expected frequencies in the different categories. And in the second goodness of fit test, we don't expect equal frequencies in the different categories. So let's go over the first example where we have an expectation of equal frequencies or equal counts in the cell. In this problem that you see, why don't you go, let's stop the PowerPoint at this point, go ahead and read the problem. So in this problem, 120 college students were polled or asked for their preferences for different types of cell phone designs, and each student was classified in one of three ways, as preferring design 1, design 2, or design 3. Our observed frequencies for the cell phone designs, we have 54 students were classified as preferring design 1. That's what they said, that's what they expressed. 38 students expressed a preference for design 2, and 28 students expressed a preference for design 3. So this is what we observe, this is what we see, this is what we got from our polling data. And these three numbers should add up to 120. Now, what would we expect if there were no preferences? If they actually had no preferences, what would we expect these frequencies to be? Well, since we have 120 people and we have no reason to expect one design is preferred to the other, then our expected frequencies would be 40 and 40 and 40. And our expected frequencies, if we've calculated them correctly, also should add up to 120. So when we look at each category of cell phone design, we see differences between observed and expected. That's to be expected. Not everyone's going to feel the same way about a particular design. But why do we have those differences? Are those differences due to sampling error? Or are those differences that we see between observed and expected due to a real, genuine preference for one type of design over another? That's the purpose of the test. So we're doing a hypothesis test to determine if the differences that you see between the observed and the expected frequencies are due simply to sampling error or are due to real preferences. We have a null hypothesis, and we have an alternative hypothesis. With chi-square, we write out the null hypothesis. Our null hypothesis, we're not going to be using symbols. Our null hypothesis is that there are no preferences for one design over another. Our alternative hypothesis would be that there are preferences for one design over another. Null hypothesis, no difference among the categories, no preferences. Alternative hypothesis is that there are preferences. There are real differences. We have the chi-square statistic is the statistic we compute. We've computed a t, we've computed a z. Now we're computing a statistic called chi-square used with nominal data. And this chi-square statistic has degrees of freedom. And the degrees of freedom equals the number of categories in the type of problem that you're doing minus 1. In this case, we have 3 categories of cell phone design. We could have 5 categories of cell phone design. We could have 10 categories of cell phone design. We have 3 in this problem. Minus 1 gives us 2 degrees of freedom for this type of problem. If we had 4 different types of menu offerings, we would have 3 degrees of freedom. If we had 5 different types of movies, categories of movies, we would have 4 degrees of freedom. The problem tells us to do this statistic test at the 0.05 level of significance. We're willing to risk being wrong, of making a type 1 error, saying that there's a difference when there really isn't one. We're willing to take a 1 in 20 or a 0.05 risk. So we have a critical value, and our chi-square critical value is going to be chi-square greater than, well, what is that? We have 2 degrees of freedom. At the 0.05 level of significance, go to your table, find the row for 2 degrees of freedom. This table is in your book. And go to the right till you see the 0.05 level of significance, and that cell says that you have to get a chi-square value that exceeds 5.991 to reject the null hypothesis. Okay, 5.991. So our formula to compute the chi-square statistic says, to compute the chi-square statistic for each cell, take the frequency of the expected, subtract it from the observed frequency, square that value, and divide by the expected frequency. And for every cell, you're going to add up the different quotients that you get when you subtract the expected from the observed, square them, and divide by the expected. Let's just look at the formula for a minute. Look at the numerator and look at the denominator. We've done this a lot with the statistical tests we've been doing so far in this class. Your numerator is a deviation score. It's an observed difference. An observed difference between expected and observed. And what we want to know is that observed difference large enough for us to say that there is a real difference, a real preference over one design over another, or is that difference due to sampling error? Well, what would we expect? That's our denominator. We have an expected frequency if there were no difference, and we have our observed difference. And if we compute the difference between expected and observed and divide by the expected frequency and add those up for each cell, we'll get a chi-square statistic. So let's do it for the first cell. For the first cell, we're going to take our expected frequency which is 40, subtracted from what we see, what students actually report. 54 of them said they preferred the design. We're expecting only 40. We have a difference of 16. I'm sorry, we have a difference of 14. We're going to square that difference, and we're going to go to divide by 40. We're going to add to that what the results from doing this analysis with cell 2. We're going to take 40, subtract it from how many students said they preferred design 2, 38, square that difference, and divide by 40. And finally, in cell 3, we have an observed difference again of 40, since there's no difference in the expected difference of 40. Subtract it from 28, square that difference of 12, and divide by 40. If you do that for each cell, you'll get a 4.9 for cell 1, plus a chi-square value of, or a quotient for cell 2 of 0.1, plus a value of 3.6 for cell 3. When we add up these three quotients, we get a chi-square value of 8.6. 8.6 is greater than 5.991, so we're going to reject our null hypothesis and conclude that there are preferences, that students have a preference for one design or another. Strictly speaking, all the chi-square test is telling you is that there is a preference for one design over another. It doesn't necessarily point to the cell or the design or the category which is the one that is preferred over the other. However, when we look at the numbers, we can see that most students prefer design 1. Or the difference between the observed and expected for design 1 is the greatest of the three. Now let's go ahead and do the second type of goodness of fit test, which is a goodness of fit test where we don't have equal expected frequencies. We expect that the expected frequencies in the cells will be different. And you'll see when you read the two problems that they give you very, very different data. Go ahead and stop the PowerPoint, read this problem, and notice the similarities and the differences between the data presented in this problem and in the previous one. The similarities are that we have a sample size. In this case, we have 200 biology students. We have frequencies that we observe, 32 A's, 61 B's, 64 C's. We have a significance level. We have categories. We have 1, 2, 3, 4, 5 categories of grades. All of those are the same. But there's one principal difference. You're shown that in the past, we expected 26% A's, 31% B's, and so on. We have data from the past which tell us what to expect. In the previous problem, we were given no such information. We were simply told there are 120 students. They were asked what they prefer. And we said, well, if there were no differences, then we would expect that the frequencies for each design would be the same. Now, in this case, we're told that in the past, here's the expected proportions. And we'll calculate the expected frequencies from that data. And so our expected frequencies are based on that information. And so we compute our expected frequencies differently in this type of problem than we did in the previous problem. We have a null hypothesis. The null hypothesis would be that the grade assignments have not changed, or there's no difference in the proportion of people getting different grades. You can write this hypothesis any way you choose. The grade assignments have not changed. Over time. Our alternative would be that they have. The grade assignments have changed. We have degrees of freedom. Degrees of freedom equal the number of categories minus 1. So we have 4 degrees of freedom. And we have a critical chi-square value that we need to exceed. In this case, if we go to our table and look at the row for 4 degrees of freedom at the 0.05 level, we need to exceed a chi-square value of 9.488. So we're going to reject our null hypothesis if the critical chi-square value that we need to exceed, if the chi-square that we compute, the chi-square that we compute is greater than the critical chi-square. The critical chi-square value is 9.488. To compute the chi-square statistic, we take for each cell the expected frequency, subtract that from the observed frequency, square that, divide by the expected frequency, and sum that up for every cell. We have 5 cells in this case that we need to sum it up for. The formula for all chi-square tests is the same. It's just what you see there. But in order to calculate chi-square, we have to determine, well, what are our observed and expected frequencies. The observed frequencies are always given to us in the problem. It's what we got from our sample. We had 200 biology students, and in 2011, 32 of that 200 got A's, 61 got B's, 64 C, 31 D, and unfortunately 12 people got F's. That's what we see. That's what we learn from our sample. That's our actual data. But now how do we calculate the expected frequencies? We said that they're not going to be the same because we have data from the past that indicates that about 26% of people get A's. Well, how many people were in this sample? There were 200. And if there are 200 people in this group of biology students, in the past, 14% got grades of A, so we would expect the same for the current class. So if we multiply 14% times 200, we will get an expected frequency of 28 A's. So what we did is we took the proportion and we multiplied it times the total number of people, and we got the expected frequency. We had 14% times 200, and it gave us 28. So now we can write in our expected frequencies for a grade of A. We would expect that 28 people would have gotten a grade of A. We see that in this class, 32 did. We have 4 more A's than would be expected. Now, is that great enough for us to say that grading standards have changed, that grades are getting lax? We need more data. 61 people got B's in this 2011 group. And in the past, 26% of students in this department were getting B's. That 26% times 200 would give us an expected value of 52. In the past, 31% got C's. 31% times 200 would be 62, would be our expected frequency. Previous data tell us that 19% of the class got D's. So what would we expect if the grading standards hadn't changed? We would expect that 19% times 200 biology students, that would have given us 38, would have gotten D, and we have 10% Fs in the past. We would expect this current 200 group, 10% of them would get Fs. That would be an expected frequency of 20. And if we add up all the expected frequencies, the total should be the same as the observed. If they're different, you made a mistake in calculating the expected frequencies. Go over it again. So now we have all the data that we need to solve the problem. We have observed frequencies, we have expected frequencies, and we can go ahead and compute this value for each cell. For cell 1, we would have 32 minus 28 squared divided by 28. For cell 2, we would have 61 minus 52 squared divided by 52, and we would do that for C's, D's, and F's. If you do that correctly, you will get a 0.57 for cell 1, to which you'll add 1.5 for cell 2, 0.06 for cell 3, 1.29 for cell 4, and a discrepancy of 3.2 for cell 5. And when you add up all of these discrepancies, you will get a chi-square value equal to 6.62. Now we don't get pluses or minuses because we're squaring numbers. So don't worry about it being a minus or a plus like we did with T or Z. They'll always be positive. But we have a chi-square value of 6.62. We said that we had to be greater than 9.488, so we cannot reject the null hypothesis. And our conclusion would be is that even though there are differences between the grades that are being assigned now and the ones in the past, and even though it looks like we have more A's and more B's and fewer D's and F's now than we did in the past, those differences are due to sampling error. Those differences aren't due to a real change in the standards, so we cannot reject the null hypothesis. Now let's go on to the second major type of chi-square test, which is the test of independence, or the test where we use a contingency table. The previous two problems, the problems that we just went over, have basically one dimension in which we have a series of categories or cells. We have a dimension of grades, and we have 5 different grade categories. We have a dimension of cell phone design, and we had 3 different designs. But in the next test, the next chi-square test, called a contingency table analysis or chi-square test of independence, we're going to have different dimensions. So as you read the next problem, notice again the similarities and the differences. In chapter 15, you learned how to determine whether 2 variables were related using a correlation coefficient. We said we had to have at least interval, most of the time we have rate or ratio data in order to determine whether 2 variables were related. We can also study relationships using nominal data through the chi-square statistic. But again, in this case, the association is between data classified in categories, where people will put into categories or where stimuli will put into categories, and where we don't have ratio or interval data. So when you read this problem, you'll see some similarities, you see differences. We have a sample. We have categories. But the big difference is that we have more than one dimension. We have a dimension of color, and we have a dimension of personality, introvert and extrovert. And what we want to determine is there a relationship between color preference and personality type? So we have two dimensions, and we want to know if there is a relationship and association. Another way of saying that is preference for color dependent on what personality type you're classified as. That's why it's also called a test, a chi-square test of independence. We have null hypotheses. We'll write it out. Our null hypothesis: there is no relationship. There is no relationship between color preference and personality. And our alternative hypothesis would be that there is a relationship between color preference and personality. We have a critical chi-square value that we need to exceed. And that chi-square value has degrees of freedom. Only in this case, the degrees of freedom in a chi-square test of independence, or a contingency table, the degrees of freedom you calculate by taking the number of categories in the rows minus 1 times the number of categories in the column minus 1. So in this case, we have two categories in the rows, so we have 2 minus 1 times, we have 4 categories in the color dimension. We subtract 1 from that, and that's going to give us 1 times 3, or 3 degrees of freedom. So to get the degrees of freedom, count up the number of rows, subtract 1, multiply that times the number of columns, subtract 1, and you'll get your degrees of freedom. So we have 3 degrees of freedom. Now we can go ahead and compute our critical chi-square value in the way we've been doing it. Find 3, go to your table, find the row for 3 degrees of freedom, and go to the 0.05 level of significance, and we need a chi-square value greater than 7.815. So we will reject HO. If chi-square is greater than 7.815. There are similarities with the previous problems where we have degrees of freedom, where we have a chi-square value. We have critical values. The major difference in a contingency table analysis, or the test of independence, is how we compute degrees of freedom. That's one of the major differences. But the major difference is how we compute the expected frequencies. So let's turn to that now. There were a total of 200 people in this study. Of that 200 people, 50 were introverts, and 150 were classified as extroverts. Our expected frequencies, remember, are always and observed should be the same. And the breakdown, I'll give you the observed frequencies of color preferences for the different personality types of the following. Of the 50 introverts, 10 preferred the color red, 3 preferred the color yellow, 15 preferred the color green, and 22 preferred the color blue. And when we add up those observed frequencies, we should get 50. And for the people who were classified as extroverts, 150 of them, 90 preferred red, 17 preferred yellow, 25 preferred green, and 18 preferred blue. And again, if we add up those totals, we should get 150. Now we might think of red and yellow as more bright, happy colors. Green and blue as more somber colors. So it looks like, just looking at the frequencies that we observe, that more extroverts are preferring red to the introverts. More extroverts prefer yellow, but more introverts, at least proportionally, seem to prefer green and blue. What makes this problem difficult is we have different numbers of introverts and extroverts. So we just can't look at the data and say, well, more extroverts prefer red because we have more extroverts to begin with. We have to look at proportions. And that's where the expected cell counts come in. In trying to get the expected frequencies, the next step should be to compute your total counts for each color. So there were 100 people who expressed a preference for red, 20 who expressed a preference for yellow, 15 plus 25 is 40 who expressed a preference for green, and another 40 who expressed a preference for blue. These totals that you see are called marginal totals. And we computed these totals by adding up the frequencies in the different cells. And what we want to know now is, what would we expect if there were 50 introverts? What proportion of them would we expect to prefer red, yellow, green, or blue? We have to consider both categories in determining the expected frequencies. The way to get your expected frequencies is to take, for any cell, let's say I want to compute the expected frequencies for red for introverts, find the total at the end of the row of that cell. In this case, it's 50. So take the row frequency and multiply it times the frequency for that cell's column, which is 100. And divide that by the total number of people in your sample. And that will give you the expected frequency. Let's do that for the cell where introverts chose red. 10 chose red, but how many would we expect? Well, the row frequency for introverts is 50. The column total for that cell is 100. And we're going to divide that by the total number of people in our sample, which was 200. And that will give us an expected frequency. 50 times 100 divided by 200 is going to equal 25. So I would expect that 25 of the 50 introverts would prefer red. However, I observe 10, so I have a difference. And now I use that same process for every cell to compute my expected frequency. To find out the expected frequency of introverts who are choosing yellow, I multiply 50 times 20, which is 1,000, and I divide by 200, and that will give me 5. To find out the expected count for green, I multiply 50 times 40, and I divide that by 200, and that would give me 10. To find the expected frequency for introverts with blue, I would multiply 50 times 40, I would divide by 200, and that would give me an expected frequency of 10. So for each cell, what I've done for 4 cells, I've looked at the total for the row, which is 50 for red, multiplied that times the total in the column, which is 100, and divided by the total sample size. And I did that for all 4 cells, and I got expected frequencies of 25 and 5, 10, and 10, and they total of 50. 50 observed, 50 expected. So it looks like I did that right. Now let's do the same thing for the extroverts. The row total is 150 for the extroverts, times the column total in the red area, which is 100, and I divide that by 200. And if I multiply 150 times 100 and divide by 200 and do that correctly, I'm going to get an expected total of 75. For yellow, I'm going to multiply 150 times 20, divide by 200. I will get an expected frequency of 15. I'll do the same for green and blue, and I get expected frequencies of 30 and 30. And if I add 75 plus 15 plus 30 plus 30, I get 150. So I have equal observed and expected frequencies. And now when I add down, I'll get 100 in my expected frequencies for red. I get 20 for yellow. I get 40 for green. And I get 40 for blue. And I have equal observed and expected frequencies, and my totals are 200 and 200. So I've done all that correctly. So now I feel good, and I'm ready to compute the chi-square. And the chi-square statistic is the same that we've been studying. To get chi-square, you take the frequencies in the expected column, frequency in the expected, in the cell for the expected, subtract that from our observed frequency, square that, divide by our expected frequency, and add that up for 1, 2, 3, 4, 5, 6, 7, 8 cells. We see similarities and differences with what we've done up until now. We have observed frequencies, we have expected frequencies. However, the observed and expected frequencies are calculated very differently for a test of independence or the contingency table. The formula is the same. Once we get the expected frequencies and the observed frequencies, we're ready to plug all those values into our chi-square formula, and we do the tedious math, and you have to do that 8 times. So in our first cell, and I'll just do it for the first one, we're going to take 10 minus 25, square that, divide that by 25, and you're going to get, that's 15 squared, which is 225 divided by 25. That gives you a 9. And if you went ahead and did that for every cell, and then added up the total for every cell, which is what that sum there indicates, you should compute a chi-square value equal to 35.63. We said that we needed a chi-square value greater than 7.815, and we certainly did that, so we are going to reject our null hypothesis. So the difficult aspect of your contingency table or your chi-square test of independence is calculating the expected frequencies. But once you have those, it's just a matter of pretty basic math. We get those expected frequencies again by taking for each cell the frequency in the row times the frequency in the column and divide that by the total number of people in the sample. That may seem like a strange way to compute expected frequency. In the previous problems we either had, where we had just one dimension, we either had equal frequencies or previous data suggested that we had unequal frequencies, but it was pretty straightforward in how to calculate it. Here we're taking the column totals, the column total for the row, the column total for the column, multiplying it times the total in the sample. And what that's basically saying is that if there were no preferences, if there were no relationships, then the major factor determining expected frequencies would be your column and your row totals. And that's what this indicates. The major factor determining expected frequencies is the total in the row and the total in the column. However, when we observe the actual frequencies, we don't see, it doesn't match necessarily the expected frequencies, and that's because there's a relationship. What determines whether someone prefers red or yellow or green or blue is the fact that there is a relationship between personality and color, and that it's not simply due to sampling error.